So what we're going to cover today is we're going to talk about skin and bone. And I'm trying to reserve 2 lectures on Friday and Monday for the endocrine system. So we have to step it out here and get through this material. We'd gotten as far yesterday as laying out the structure of skin. And I'll do that again and lay it out quickly, talking about the stratified squamous epithelium of the epidermis, emphasizing that many of those cells are dead. The only living cells in the epidermis are those that are sitting right along the stratum basale. Those are the dividing cells, and they are then in turn giving rise to all the cells that lie above the stratum basale. Then we'll talk about the idea that the stratum basale is the layer of cells sitting right above the dermis being connective tissue proper. And then I want to spend some time on melanocyte function. Melanocyte function, the melanocytes are a separate set of cells. They come from neural crest, and they sit at the interface between the dermis and the epidermis. And their function is to secrete melanin. And the melanin then is taken up by the keratinocytes in the epidermis and gives skin its color. And there's an interesting history of where these came from and why some of us have light skin and some of us have dark skin. And I want to tell you that story. Then we'll take and extend this idea into the appendage of skin, and particularly we'll talk about hair. We could almost as easily talk about nails or hooves, because these are going to be keratinocytes that are modified. In the case where we have surface keratinocytes making skin, we have another kind of keratinocytes that are generating the keratinocytes that contain keratin that's unique to hair, or keratin that's unique to your fingernails or toenails, or in the case of animals, to hooves. And then we'll move on and talk about bone as an organ, and we'll see that bone is truly an organ because it's not only composed of connective tissue in the form of osteocytes, these osteocytes which have secreted collagen and calcium phosphate, also known as hydroxyapatite, but they're also innervated and they're vascularized. And we know they're innervated. If you've ever broken a bone, you know they're innervated because it hurts. And so these are characteristics of more than one tissue. These are tissues working in concert. The tissues working in concert for skin were an epithelium and a connective tissue proper, but now here we're working toward the idea of bone also being an organ. We'll draw out a long bone. We're just going to have an example of a bone. If you take a gross anatomy course, you'll get down into the nitty-gritty of the different kinds of bones, flat bones and irregular bones and all of that. But what I want to do here is simply draw a generalized bone, and then we're going to divide the bone into the 2 ends of the bone called the epiphyses, and then a shaft in between called the diaphysis. And we'll see at the ends of the bone there are these articular surfaces. The long bones will fit into joints. And because they fit into joints, they have a surface on them which is covered with hyaline cartilage. These are the articular surfaces. We're going to see, though, that within the bone itself there are 2 major kinds of bone. We're going to divide the bone into spongy bone, sometimes known as trabecular bone, and the spongy bone is constructed from millions of individual struts. But osteons are forming the compact bone. And what we'll see is that the spongy bone is relegated to the epiphyses largely, and a narrow region around the central cavity. But the osteons of the compact bone are lying along the edge. And what we'll see then from this is we'll distribute weight, because after all, that's what bone is meant to do. If I'm standing here, I'm distributing weight down through my femur and then through my tibia and fibula. But they'll distribute weight, and they're distributing the weight through the spongy bone in the head of my femur, down through the compact bone, which is around the edges of the medullary cavity. And we're going to think a little bit about how that weight will be distributed. And if there's time, we'll talk about bone growth. Our bones grow longer because there are cartilage cells called chondrocytes in a region called the growth plate. In long bones, the growth plates reside between the diaphysis and the epiphysis. And bone growth occurs by the chondrocytes dividing and pushing the epiphysis away from the diaphysis. And then about age 18 or 20, those chondrocytes die, and they're replaced by osteocytes that lay down bone. And that's the end of growth. You don't grow after that. But we're not done remodeling bone. We remodel bone throughout life. And throughout our lives, we're going to have osteocytes and osteoblasts that are creating bone. We know this to be true because if we break a bone, it will heal. And it heals because we can lay down new bone cells. The new bone cells can secrete collagen and then subsequently hydroxyapatite and reform the bone. But under normal circumstances, the bone is constantly turning over. And it's turning over as the osteocytes lay down bone and as the osteoclasts destroy the bone. The osteoclasts are these really interesting cells, and they basically wander around in the bone and they release acid. And as they release acid, they're solubilizing the calcium phosphate. The calcium phosphate is solubilized into phosphate ion and calcium ion at low pH. So we'll generate low pH regions between the osteoclast and the bone to mobilize that calcium. And we do this because we have this readily available storage of calcium in the bones. And we need to maintain our plasma calcium concentrations in a very narrow range. And so what we'll do is we'll use the osteoclasts to break down the bone, mobilize the calcium, and then the osteocytes can come in and refill those areas. But we're doing this so that we can maintain a constant level of calcium in the plasma. And that's under hormonal control, and we'll discuss that a little.